Good day everybody. Today we will be learning basics of pipe stress analysis. This presentation is made by What is Piping team. The main points that will be covered in this presentation are objectives of pipe stress analysis, that is what is the reason for performing pipe stress analysis, then governing codes and standards, various codes and standards that govern the pipe stress analysis process, then stresses in a piping system, the causes or reasons for piping stress generation, then reducing piping stresses, means what are the methods that can be followed to reduce, or how piping stress analysis helps in reducing piping stresses. Then basic allowable stresses, the material allowable stresses as given in various codes. Then loads on a piping system, various kinds of loads that are generated in the piping systems, which in turn generates piping stresses. Now next, project specifications and guidelines. The workflow diagram means how where piping stress fits in EPC organizations along with various other organizations. And finally, stress criticality and analysis methods. Let's start with objectives of pipe stress analysis. We all know that piping stress analysis is a very important activity in piping design. All the critical lines need to be validated by piping stress engineers. Basically, piping stress analysis ensures structural and operational integrity of the piping system. Structural integrity means it ensures the design adequacy for the pressure of the carrying fluid, and it prevents failure against various loading conditions in the life cycle of the plant by limiting stresses below code allowable values. And what is the term operational integrity means? It means stress analysis limits nozzle loads of the connected equipment within allowable values given by various codes or standards, avoid the leakages at joints, and limiting sagging and displacements within allowable values. At the same time, piping stress analysis ensures that design is optimum, means avoiding excessive flexibility or high loads on supporting structures. So stress analysis aims towards an optimal design for piping or structural considerations and make the design economic. Let us see what are the various codes and standards that govern the piping stress analysis. Codes and standards specify minimum requirements for safe design and construction by providing material, design, fabrication, installation, and inspection requirements. Various codes and standards govern the piping stress analysis of refinery or process piping. Those codes are ASME B31.3 process piping code, then ASME B31.1, that is power piping code. All power generation pipings are designed based on this code. API 610 for centrifugal pumps. We get equipment nozzle allowable loads from this code or this standard. Then positive displacement pumps are designed based on API 676. Centrifugal compressors are designed as per API 617. Reciprocating compressors by API 618. Steam turbines by NEMA SM23 or API 612. Air-cooled heat exchangers by API 661. Fired heaters by API 560. Flat bottom welded storage tanks by API 650. Heat exchangers by TEMA. TEMA means Tubular Exchangers Manufacturers Association, or it may be vendor specific as well. Vessels or columns, normally vendor specific. For liquid and gas pipelines, ASME B31.4 and ASME B31.8. And finally, for GRE piping, ISO 14692. All these codes provides all the equations required for piping stress analysis or allowable nozzle loads, for which we have to maintain the nozzle interface connection. Now, stresses in a piping system. From the start or from the beginning of this presentation, we are talking about stresses. Now, how these stresses are generated in a piping system. There are various sources from which the piping stresses are generated, like weights, internal or external pressure, temperature change, and various occasional loads like seismic disturbance, PSV discharge, wind, slug flow, surge flow, even forces due to vibration also causes stresses in a piping system. Now, sustained stresses. Sustained stresses are the stresses generated by sustained loads. Pressure and weight, these two are known as sustained stresses because these two loads are present continuously throughout the plant's operating life. Now, resistive force arising out of sustained stresses balance the external forces keeping the system in equilibrium. That's why sustained stresses are called primary stresses. Exceeding the sustained allowable value causes catastrophic failure of the system. If we cannot keep the system within allowable, then it may cause catastrophic failure of the piping system. Now, allowable value for this sustained stress is given by the code as per clause 302.3.5 of ASME B31.3. The sum of the longitudinal stresses SL, that is the calculated stress generated due to sustained loads, that is pressure and weight, that is termed as SL in any component in a piping system due to sustained loads, that is pressure or weight, shall not exceed SH. What is this term SH? SH is the basic allowable stress at the metal temperature for the operating condition being considered. So SH is the value that we have to select from the code based on maximum design temperature. Now, as we are telling that there are two kinds of load that generate sustained stress. One is pressure stress and other is weight stress. This pressure stress are taken care of by calculating and selecting proper pipe thickness. Code provides us the guidelines or equations for calculating this pressure design thickness T. As per this code, clause 304.1.2, the pressure design thickness T of a straight pipe can be calculated using these equations. Here, P is equal to internal design pressure, D is equal to outer diameter of the pipe, S is equal to allowable stress at design temperature, E, Y, W, those are various factors that are obtained from the code itself. Now, once this pressure design thickness T is calculated based on these equations, we have to add the corrosion and erosion allowances with this T to get Tm. This is minimum required thickness considering corrosion and erosion allowances. Next, we have to add the manufacturer's tolerance, also known as mill tolerance, with this TM value. For seismic pipes, normally 12.5% negative mill tolerance is considered. So by dividing TM by 0.875, we can get this value. And for welded pipes, various standards provides various values. Normally 0.3 mm is the standard value. So that value we have to add with this TM to calculate or to get the actual required thickness. Now, as the pipes are designed based on standard schedules or standard thicknesses, so we have to select the next higher schedule based on availability. If you want to know more about this pipe thickness calculation methodology, kindly refer this article in whatispiping.com website. There I have explained all these terms clearly and how to calculate the pipe thickness for internal design pressure. Now, how to calculate the sustained stresses? For that also code provides us the equations. Clause 320.2 of ASME B31.3 provides the equation for sustained stress calculation. As per that, SL is root over of SA plus SB whole square plus 2ST square. It again gives the formulas for equations for calculation of SA, SB. I suggest to refer to the code clause 320.2 for proper understanding and explanation of all these terms. Let's move on to expansion stress. We all know that pipes carry fluids at temperature different from the installation temperature. So there will be change in pipe material length, and we studied in our mechanical engineering that a change in length of a pipe of length L due to temperature change delta T is given by delta L is equal to L alpha delta T, where alpha is equal to coefficient of thermal expansion. Now B31.3 provides two alpha values denoted by A and B in their table C1 and C1M. Table C1 provides values in FPS unit and table C1M provides values in metric unit. So what is the difference between A and B? The coefficient A denotes the mean coefficient of linear thermal expansion between 70 degree Fahrenheit to indicated temperature. Its unit is microinch per inch per degree Fahrenheit. Whereas the coefficient B denotes the total linear thermal expansion between 70 degree Fahrenheit to indicated temperature. So for a specific temperature, using the value B, we can get direct thermal growth from installation temperature. Now, expansion stress will be generated in the piping system only if the free thermal growth due to temperature change is restricted. Now, we all know that all piping systems are connected to some equipment or some supports restrict their free thermal movement, so expansion stresses will be generated. These stresses are called self-limiting or self-relenting stresses and falls in secondary stress category. Now SIF, that is stress intensification factor, due to change in geometry or in cross-sectional area of the piping systems, stresses are intensified at various locations. The stress intensification factor is defined as the ratio of the maximum stress intensity to the nominal stress. Code B31.3 in its Appendix D provides various formulas for calculating SIFs for standard items like elbows, T connections. And also there is one code B31J that also provides SIF or stress intensification factor values. Now, how to calculate these expansion stresses? This is called, as per code, displacement stress range. So this displacement stress range due to thermal expansion is calculated based on equation 17 from clause 319.4.4, which is specified as SE is equal to root over of SA plus SB square plus 2ST square. This equation is same as per sustained stress calculation equation, but the terms are totally different. So it is suggested that you refer to the code clause to understand the difference between the equations or terms used in sustained stress as well as expansion stress. Now this calculated expansion stress AC has to be within SA, that is allowable displacement stress range. Code also defines this SA as F into 1.25 SC plus 0.25 SH or F into 1.25 SC plus SH minus SL. Here also code provides two equations, equation 1A and equation 1B. In the second equation, the allowable stress is more That is valid only when SH is greater than SL. That is, in second case, the stress calculation is becoming somewhat liberal due to higher allowable values. That's why the second equation is called liberal stress allowable equation. Here F is stress range reduction factor due to cycles or cyclical operation, that is fatigue consideration. Now stresses due to vibration. Code does not explicitly explain the stresses generated due to vibration, and vibration can occur in various forms. That's why no general method is available for its resolution. Some may require dynamic analysis, modal analysis. Some may require field vibration measurements in the form of FFT plots or fast Fourier transform plots. Even process inputs like flow conditions, throughput, etc. are required to solve vibration problems. These are normally solved by engineering judgment and from experience. Now, what are occasional stresses? Occasional stresses acts for a shorter period of time, as per code normally less than 10% of the total working period. Various occasional stresses can be generated in a piping systems like wind stresses, seismic stresses, PSB discharge stresses, slug flow, surge flow, etc. Now, as per code ASME B31.3, clause number 302.3.6, the sum of longitudinal stresses SL due to sustained loads such as pressure and weight, as well as due to occasional loads such as wind, earthquake, or other occasional stresses should be less than 1.33 times the basic allowable stress SH. SH we already defined earlier. Means for occasional stresses, we have to make the system safe for sustained plus occasional stresses, and that allowable value is less than equal to 1.33 times SH. Let's see what are the methods or how these piping stresses can be reduced. As we already discussed, that stresses generated due to pressure is already taken care by calculating or selecting proper pipe thickness. So to avoid the generation of high stresses due to weight, we can provide supports. Normally, support span is devised by various standards like MSA standard or project specific standards. So providing proper supporting weight stresses can be avoided. For thermal stresses, we have to provide flexibility. This can be provided in form of expansion loops by providing offsets, introducing elbows or bends, sometimes by using expansion joints. Now code says that flexibility check has to be performed when this equation given by clause 319.4.1 of ASME B31.3 is not satisfied. Here D is equal to outside diameter of the pipe, Y is equal to resultant of total displacement strength, L is the developed length of piping between anchors, U is the anchor distance, straight line between anchors, EA is the modulus of elasticity at 21 degrees centigrade, and SA is the allowable displacement stress range. Code also says if any system is directly replacing, right, like to like the replacement for any operating plant that is operating for a considerable period of time, then also without flexibility check we can accept that system. Now basic allowable stress. Basic allowable stress is the SC or SH values that we normally select from those tables, table C1 and table C1M. Now code decides that based on the minimum of 1/3 of ultimate tensile strength at operating temperature, 1/3 of ultimate tensile strength at room temperature, 2/3 of yield tensile strength of the material at operating temperature, 2/3 of YTS of material at room temperature, 100% of average stress for creep rate of 0.01% per 1000 hours, and for structural grade materials, basic allowable stress is equal to 0.92 times of the lowest value obtained from 1 through 5 hours. So code calculates all these values and chooses the minimum of these values, and we directly get it in table C1 or table C1M. Now, what are the loads on a piping system? Loads can be grouped in two categories. One is called static loads that does not vary with time, and one is called dynamic load that varies with time. What are these static loads? Weight and pressure that generate sustain stresses. Then hydro test. All systems before commissioning need to be hydro tested for checking any leakage possibility. This is also called pressure test. So this is also a kind of static load. Then thermal expansion due to change in temperature, and settlement. Sometimes due to heavy weight, soil may settle down due to, normally for tank and other big size equipments, settlement occurs. So all these are static loads. Let's move on to dynamic loads. Dynamic loads vary along with time. So these loads are time dependent. Examples are seismic, wind, PSV, slug flow, water hammer, and vibration. At different instant of time, the values will be different for this kind of loads. Now, project specification and guidelines for performing stress analysis. Various project specification and guidelines will be required. Normally, piping material classes, piping design and plant layout guidelines, piping stress analysis work instruction or guidelines, piping stress critical line list, pipe support standard means how pipe system has to be supported, and stress analysis work procedures. All these guidelines will be required for performing pipe stress analysis. Let's learn about the workflow diagram of pipe stress analysis. Piping stress analysis is a part of piping team. All the basic inputs we receive from the piping team like piping stress isometrics and other data. Now with civil team, we are connected for soil characteristics for performing underground or buried piping stress analysis. From mechanical department, we receive equipment G drawings or nozzle allowables. From process department, we get PNID and line list or line designation table, that is parameters for stress analysis. From instrumentation department, we get the instrumentation data like PSV, reaction force, and other data. And from outputs, we provide as piping stress analysis report and markup stress isometrics that we provide clit loads, nozzle loading information if more than allowable to mechanical department. Then with structural department, we provide the support loads for their support design. Then for site or field directly approved stress ISOs means whatever recommendation stress team provides, those are updated and then final isometrics are sent to site for erection. Now stress criticality and analysis methods. So from PNID, all the lines we do not analyze. It is decided by project design basis or project flexibility specification that which lines to be analyzed and what will be the analysis methods. Normally three types of analysis methods are used. One is computer analysis using softwares. Second is visual or computer analysis, and third one is visual inspection. All lines in the line list or PNID are categorized into various based on their criticality into various groups like high critical lines. These are steam turbine, compressor connected lines. Moderately critical lines like pump or AFC connected lines. Then low critical lines slightly lower based on temperature and pressures, and non-critical lines which have very less temperature or pressure, normally side rotated. Highly critical and moderately critical are must to be performed by computer software programs. Low critical lines, depending on equipment connection, can be visual or computer analysis, and non-critical lines we do not analyze, only for supporting we inspect visually. Now regarding all these methods, slowly we will be learning in our next videos. So for these basics of piping stress analysis, this is it. So thank you, and to get more updates about future videos, kindly subscribe to our channel. This is the name of our channel, Scissor 2 Piping Stress Analysis, with this logo. Thank you.